Have you ever just hit a wall with a problem that felt so complex you figured it would take a million years to solve? A puzzle with just a ridiculous number of possible answers? Well, today we're going to dive into a really clever strategy for cracking exactly those kinds of challenges. Okay, picture this. You're dropped into a giant, incredibly complex maze. There are countless paths, forks in the road, dead ends everywhere. Your one goal is to find the exit. So, how would you even start? This is the exact challenge that so many big computational problems face, everything from scheduling flights to cracking codes. So, the most obvious way to solve that maze problem is what we call brute force. And it's pretty much what it sounds like. It's like deciding you're going to walk down every single path, from the very beginning to the very end, one by one, until you just happen to stumble upon the exit. Yeah, the brute force method generates what's called a Cartesian product. You can just think of it as a massive, super messy list of every possible combination that exists. But for any problem that's even a little bit complex, this method isn't just slow, it's often computationally impossible. You would run out of time and memory long before you ever found the answer. So if trying every single thing is basically a dead end, what's the alternative? Well, this is where our hero comes in: backtracking. And it's not about working harder, it's all about working smarter to get through that maze. The main idea here is actually really simple, but it's super powerful. Instead of running down an entire path just to see if it works, backtracking builds a solution one piece at a time. It takes the step, checks if it's still on a valid track, and if it's not, it does something brilliant. It goes back. It backtracks to the last choice it made and just tries a different option.
Okay, so how does this actually play out in practice? Well, the logic is this really elegant loop of just 3 key moves. First, you advance. You make a choice and you move forward. Then you check. You ask yourself, okay, based on this step, am I still on a path that could actually lead to a real solution? This part is absolutely crucial. And finally, you react. If the check passes, great, you keep advancing. But if it fails, you immediately backtrack and try something else. You don't waste another second on a path you know is doomed from the start. Now that check step, it has a name: the continuation condition. And honestly, this is the algorithm's secret weapon. By defining a simple set of rules, we can instantly figure out if a path is worth exploring any further. It's what allows us to prune these huge, useless branches from our search, and that saves an incredible amount of time. So here we see that advance move in action. The algorithm tries a value, the continuation condition is met, it's following all the rules, so we lock that choice in and just move on to the next step in our potential solution. But what happens when we hit a wall? Well, if a new value fails the check, it violates our rules. The algorithm doesn't panic, it just recognizes a dead end. It abandons that attempt, retreats back to the previous step, and tries the next available option. No time is wasted on a path that can't possibly work.
All right, enough theory. Let's look at a classic example. Generating all the unique orderings, or what we call permutations, of the numbers 1, 2, and 3. The rule here is super simple. In any solution, each number can only show up one time. So, the algorithm starts with a completely empty slate. Its first move is just to pick the first available number, which is 1. The continuation condition is met, so our potential solution right now is just 1. Now for the second position. The algorithm, being very systematic, again tries the first possible number, 1. Our path that we're considering now becomes 1, 1. But now we have to do that crucial check and fail. The continuation condition, that all numbers have to be unique, is violated. This right here is the magic moment. A brute force method might have kept building on this flawed path, but backtracking stops immediately. It knows that nothing starting with 1, 1 can ever be a valid solution. So what does it do? It backtracks. It undoes that last step and tries the next available number, which is 2. Our new path is 1, 2. It runs the check again. Does this path follow the rules? Yep, the numbers are unique, we can advance. The algorithm just keeps doing this advance, check, react, and it quickly finds the next valid number, 3, to complete the sequence. And there you have it, 1, 2, 3, our first valid solution. Now, the algorithm doesn't stop here. It'll backtrack again to efficiently find all the other permutations, like 1, 3, 2. This might seem like just a neat trick for number puzzles, but this exact logic is what powers some incredibly complex real-world systems. Seriously, Anytime a problem requires finding a valid setup out of millions of possibilities, backtracking is the go-to tool. Think of a Sudoku solver. It's checking if a number is valid in its row, column, and square before it moves to the next empty cell. Or software that finds every single anagram for a word. It's used for complex logistics, like scheduling flights without conflicts. And even in AI, helping a video game character find the smartest path across a map by exploring routes and backing away from dead ends. It really is a fundamental problem-solving powerhouse.
Backtracking's entire philosophy is just about efficiency. It's not about finding an answer through sheer force, but through intelligent elimination. By refusing to explore paths that are guaranteed to fail from the start, it dramatically reduces the size of the problem. And that leaves us with a pretty fascinating thought. In computation, and maybe in life, sometimes just relentlessly pushing forward isn't the answer. Maybe the most effective way to solve our most impossible problems is having the wisdom to recognize a dead end and the courage to take a step back and try a different path.